dark openings are at the focal point of cosmic systems, and those are ordinarily enormous dark openings, millions or billions of times the mass of the Sun. All through the years, physicists have relied upon a mix of hypotheses, like general relativity, quantum mechanics, and the Standard Model, to open the privileged insights of our universe. These hypotheses have successfully made sense of astronomical peculiarities, shedding light on how divine bodies act and the perplexing nature of particles at the littlest scales. Without hypotheses guiding us, there would be so many questions out there in the universe that would go unanswered. However, consider the possibility that we've been mixed up this whole time. Brian Greene has at long last ended his silence and said that all advanced speculations are off base, and that we're living inside a dark opening. Go along with us as we translate what Brian Greene was discussing. 0.4 A long time back, dark openings were rotating around one another, going close to the speed of light, banging into each other, and creating a tsunami in the texture of space. This disclosure might potentially change all that we've at any point had some significant awareness of our reality. In the realm of hypothetical material science, few voices carry as much weight as that of Brian Greene. No one can deny his excellent contributions to the field, especially in the domain of string hypothesis. His profundity of knowledge, deliberate focus, and ability to convey intricate ideas to both specialists and the general public have established him as a leading expert in the scientific community. Greene's expertise extends far beyond his impressive research accomplishments. He has an exceptional talent for unraveling the mysteries of the universe through his books, lectures, and media appearances. Through his best-selling works like The Elegant Universe and The Fabric of the Cosmos, he has successfully bridged the gap between the recondite world of theoretical physics and the curiosity of the wider public. His unique ability to distill complex ideas into accessible narratives for everyone has empowered countless individuals to engage with significant scientific concepts. In this way, he has also been responsible for growing the scientific community. However, it's Greene's academic background and professional achievements that cement his position of authority. As a professor of physics and mathematics at Columbia University, he has mentored and inspired numerous aspiring physicists, fostering a new generation of scientific thinkers. His research contributions in string theory, a framework aiming to unify the fundamental forces of nature, have moved the field forward and earned him broad recognition from peers and experts worldwide. So, when a man like this says something, the world listens. And when he personally claims that all of the modern theories we had always looked to for answers are completely wrong, that we're not just inside our planetary group but inside a dark opening, it causes a stir. All that we've known about our existence is false, and this whole time we've been inside a dark opening ourselves. But how is it that this could be? Could current theories be this wrong? The idea that our universe might exist inside a dark opening has actually been explored by scientists for some time now. Over the years, several theories and ideas have emerged to suggest how our universe could be connected to, or have originated from, dark openings. One idea put forward by some physicists is that every dark opening may give rise to a new universe. This idea is based on the concept of torion, which proposes that inside each dark opening, another universe is created. By this perspective, dark openings act as vast gateways, leading to the birth of new universes within them. Another idea suggests that our visible universe is inside a dark opening, which itself exists as part of a larger parent universe or multiverse. In this view, dark openings serve as portals to other regions or dimensions of spacetime, including different universes or realities. The singularity, the infinitely dense core of a dark opening, is also seen as a possible source for the birth of new universes. Some experts propose that the singularity inside each dark opening could have resulted in our own universe. This idea draws parallels between the initial state of our universe, often referred to as a singularity, and the concept of black hole singularities. Another intriguing theory is that our universe originated from a dark opening that resides inside another universe. According to this hypothesis, when a dark opening forms through the collapse of a dying star, a parallel universe is simultaneously born through a white opening located on the other side of a hypothetical wormhole. This idea connects the formation of dark openings to the creation of new universes. But that's not all. Some theories even suggest that our universe could exist inside a higher-dimensional dark opening. This perspective suggests that our universe began as a singularity, a point of infinite temperature and density, similar to how scientists describe dark openings. The idea suggests that our universe is trapped inside the event horizon of a four-dimensional dark opening. This would mean that we couldn't even tell that we're inside a dark opening, no matter how hard we try. But you see, this hypothesis contradicts everything we know about the way our own universe works, things that we've already studied and proven with modern physics. Modern physics encompasses a range of theories that aim to explain the fundamental nature of the universe, from its largest structures to its smallest constituents. These theories have been developed through rigorous scientific investigations and have provided remarkable insights into the workings of the universe. At the heart of modern physics lies the framework of quantum mechanics, which describes the behavior of particles at the atomic and subatomic scales. It introduced a new way, distinct from classical physics, which relied on strict laws and precise measurements, by revealing the nature of the microscopic world. One of the key concepts in quantum mechanics is wave-particle duality. It reveals that particles like electrons or photons can exhibit both wave-like and particle-like properties. This means that they can act as discrete particles with definite positions and momenta, yet they can also display wave-like qualities like interference and diffraction patterns. This duality is captured by the mathematical formulation of quantum mechanics, which uses wave functions to describe the probability distribution of finding a particle in different states. Another astonishing aspect of quantum mechanics is superposition. According to this principle, particles can exist in multiple states simultaneously, a phenomenon not observed in classical physics. For example, an electron can be in a superposition of spin-up and spin-down states, meaning it exists in both states at once until a measurement is made, collapsing the wave function into a definite state. Quantum mechanics has revolutionized our understanding of the microscopic world. Preparing for technological advancements like lasers and atomic power, which rely on the principles of quantum mechanics, it's clear that quantum mechanics explains the world as we know it from a microscopic perspective, the very building blocks of life. Since their discovery, we've understood that everything operates in a certain way, which should represent the truth. However, that's not entirely the case. There are aspects of different theories that have always explained how Earth and the universe truly function, like general relativity, which describes gravity as the curvature of spacetime caused by matter and energy. It provides a mathematical framework to comprehend the behavior of massive objects, including planets, stars, and galaxies. The theory successfully explains a range of phenomena, such as the precession of Mercury's orbit, the gravitational lensing of light, and the expansion of the universe. Yet, even general relativity breaks down under extreme conditions, such as at the center of black holes or during the early moments of the Big Bang. This necessitates a more complete theory of gravity. The Standard Model of particle physics takes this understanding even further. It's an exceptionally successful theory that provides a comprehensive framework for understanding the fundamental particles and forces that constitute the universe. It incorporates three of the four fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force. Each of these plays a crucial role in how our universe functions. The electromagnetic force is responsible for interactions between charged particles, such as electrons and protons. The weak nuclear force, on the other hand, is involved in processes like radioactive decay and certain types of nuclear reactions. The discovery of the W and Z bosons, which mediate the weak force, provided strong experimental evidence supporting the validity of the electroweak theory within the Standard Model. The strong nuclear force is responsible for holding atomic nuclei together. It governs the interactions between quarks, the fundamental particles that make up protons and neutrons, through the exchange of gluons. Quantum chromodynamics, a branch of the Standard Model, describes the behavior of the strong force and has been rigorously tested in experiments. So, the theories we're discussing here are not just theories, they've been repeatedly proven to be the real deal. Additionally, the Standard Model even predicted the existence of the Higgs boson, a particle associated with the Higgs field. The Higgs field is thought to be the mechanism that gives particles their mass through interactions with the field. In 2012, experiments conducted at the Large Hadron Collider confirmed the existence of the Higgs boson, further validating the Standard Model. However, despite its successes, the Standard Model still has its limitations. One major limitation is its inability to account for the existence of dark matter and dark energy, which are believed to make up a significant portion of the universe. Dark matter, a form of matter that doesn't interact with light or other electromagnetic radiation, is inferred from its gravitational effects on visible matter. Dark energy, on the other hand, is proposed to explain the observed accelerated expansion of the universe. Understanding the nature of dark matter and dark energy remains an active area of research in the world of science, and they are also thought to be fundamental components of black holes. Yet, the challenges don't end there. There's also the issue of attempting to unify the gravitational force with the other fundamental forces. The Standard Model does not include a description of gravity, which is instead explained by general relativity, a separate theory. This is where perhaps physicist Brian Greene has a point. His expertise lies in exploring the fundamental nature of the universe, seeking a unified theory that encompasses all forces and particles within a single framework. One of Greene's notable contributions is his work on mirror symmetry, a concept within superstring theory. Mirror symmetry establishes a profound connection between two seemingly distinct Calabi-Yau manifolds, which are higher-dimensional geometrical spaces. This discovery revolutionized the understanding of string theory by revealing unexpected relationships between seemingly different mathematical representations of the universe. These small differences provide a path for Greene's theory as well. Perhaps, the differences, though subtle, could add up, and we might discover that we are not just floating through space, maybe we've been inside a black hole this entire time. Now, here's where things get even more interesting. There's a reason why black holes are such a hot topic in the world of science. They get more mysterious the more you learn about them. According to current theories, a black hole is a region in space where the gravitational pull is so overwhelmingly strong that nothing, not even light, can escape its grasp. This extraordinary characteristic arises from the extreme concentration of mass within a compact volume, causing spacetime to become severely warped in its vicinity. What's even more fascinating is that black holes exhibit properties that set them apart from any other known objects in the universe. One of their defining features is their incredible density. The mass of a black hole is compressed into an infinitesimally small region, resulting in an enormously powerful gravitational field. This gravitational force is so strong that even particles traveling at the speed of light cannot overcome it, leading to the formation of an event horizon, a boundary beyond which nothing can return. Despite their immense gravitational pull, black holes have only three properties: mass, spin, and electric charge. Mass is the primary defining characteristic of a black hole and determines its gravitational influence. Spin, which is akin to an object's rotation, describes the angular momentum of the black hole. Black holes don't spin in a simple, straightforward manner, they twist and rotate on an angle, which is also one of the reasons why black holes can differ from one another. Even the slightest differences in their angular momentum can lead to significant variations. Theoretical physicists have developed several models to describe different types of black holes, but in most cases, stellar black holes are the most common variety. They form from the gravitational collapse of massive stars at the end of their life cycle. Mass dark openings commonly range in mass from multiple times to several hundred times that of our Sun. Their development involves a destructive event wherein the core of a dying star collapses under its own gravitational force, giving rise to a compact object with an extraordinary gravitational pull. Beyond stellar mass dark openings, different types of dark openings exist in theory, including very large dark openings and primordial dark openings. Very large dark openings are believed to reside at the centers of most galaxies, including our own Milky Way. They contain millions or even billions of times the mass of our Sun, yet the exact mechanisms of their formation remain a subject of ongoing research. Primordial dark openings, on the other hand, are speculative entities that may have formed shortly after the Big Bang. They would have originated from fluctuations in the early universe and could range in mass from tiny to superenormous. Although the more complicated dark openings are a bit more challenging to study, it doesn't mean that scientists aren't actively studying every dark opening they can possibly find. Astronomers use an array of methods to detect and study dark openings, allowing us to dive deeper into the mysteries of these cosmic entities. One approach involves detecting the gravitational influence exerted by dark openings on surrounding matter. Observing the motion of stars and other luminous objects helps astronomers identify areas where the gravitational pull is particularly strong. For example, at the center of our Milky Way galaxy, astronomers have observed stars orbiting an apparently empty spot, indicating the presence of a supermassive dark opening. Another method involves studying the material that falls into a dark opening. As matter spirals around the dark opening, it forms an accretion disk, a disk-shaped structure made of gas and dust. The intense gravitational forces and friction within the disk generate immense heat, causing it to emit radiation across various wavelengths, including X-rays. This helps astronomers gain valuable insights into the characteristics and behavior of the dark opening. In some cases, astronomers can even directly detect the bright emissions from the material falling into a dark opening. As matter accelerates near the dark opening, it gains incredible speeds, producing extreme heat and emitting copious amounts of radiation. This emission can be detected across different wavelengths, from visible light to X-rays. Analyzing this radiation allows scientists to interpret critical information about the properties and dynamics of dark openings. Not all methods of studying dark openings are so direct. The motions of nearby stars also offer another way to detect dark openings. Researchers can also study the precise movements of stars in the vicinity of a suspected dark opening. With that information, astronomers can recognize irregular patterns or deviations that signify the presence of an extraordinarily massive object. These observations provide valuable clues about the mass and location of the dark opening, enhancing our understanding of its gravitational influence. The detection of gravitational waves has opened up a new avenue for studying dark openings. Gravitational waves are ripples in the fabric of space-time caused by the spectra to model the emissions from galaxies and dark openings at unique frequencies. This method enables them to identify the signatures associated with active dark openings, providing a deeper understanding of their prevalence and characteristics in the universe. Once dark openings are detected, scientists use various techniques to study them in detail. They observe the motion of stars and gas in the vicinity of the dark opening, which provides insights into its mass and gravitational effects on its surroundings. This allows them to gather valuable information about the physical processes occurring near dark openings. Reverberation mapping is another technique used to study dark openings. This method involves measuring time differences between emissions from different regions near the dark opening. By analyzing these time delays, astronomers can map out the orbits of gas and photons around the dark opening, unraveling the dynamics of the accretion disk and the interaction between matter and radiation. State-of-the-art experiments, such as the Event Horizon Telescope, EHT, have also revolutionized our ability to study dark openings. The EHT is a global network of radio telescopes that work together to create an Earth-sized virtual telescope, enabling scientists to capture images of dark openings with a resolution that was previously unimaginable. This was the telescope network that successfully imaged the supermassive dark opening at the center of the galaxy M87, providing visual evidence of the event horizon. Although this was a known fact before, being able to see what scientists have described for decades is something else entirely. Now that we've actually seen a dark opening, you'd think that it's all clear, right? But that's where Brian Greene shakes up all that logic. His provocative theory suggests that our universe exists inside the bounds of a dark opening. This claim actually stems from the complex interplay between general relativity, quantum mechanics, and the properties of dark openings. According to Greene's reasoning, if we consider the laws of general relativity, particularly Einstein's theory of gravity, and apply them to the vast scale of the universe, intriguing possibilities emerge. Dark openings, characterized by their intense gravity, can significantly distort space and time in their vicinity. Just inside a dark opening's event horizon, where the gravitational forces are strongest, the fabric of spacetime becomes highly curved, leading to some pretty interesting effects. Green suggests that if our universe were inside a dark opening, the gravitational force acting within it would be responsible for the expansion and structure we can observe. In this scenario, the universe's expansion could be attributed to the gravitational pull exerted by matter falling into the dark opening from outside regions. The gravitational collapse of matter could also account for the formation of galaxies, stars, and other celestial structures that we've been studying for millennia.